Let's analyze the steady-state error of simple feedback systems. As we saw in the last video, in these systems, the acting error and the true error, that is, the difference between what we want and what we have, are the same. So EA of S is equal to E of S. Okay, we're used to the formula relating Y of S with R of S, the formula of the closed loop. Do we have a formula relating the error E of S with R of S? Well, we don't, but we don't really need one, just as we don't need this formula, because finding the relation between two signals in a closed loop takes no more than 10 seconds. All we have to do is to find an expression in which only the two signals involved appear. So here E of S is equal to R of S minus Y of S, but Y of S is just P of S times C of S times E of S. Here we have the two signals involved. Now we rearrange this like that. 1 plus P of S, C of S, this is equal to R of S. And from here we already have the formula. That's 1 over 1 plus P of S, C of S. So if we are interested in the steady state error, we can apply the final value theorem to this signal in order to calculate it. So E steady state, which is the limit when t tends to infinity of E of t, this is the limit when s tends to 0 of s times this function, this signal here, 1 over 1 plus P of S, C of S, R of S. Now let's combine these two functions in just one that will denote with R of S, and this function is called the open loop transfer function. So given that, our formula for the steady state error, ESS, is equal to the limit when s tends to 0 of s times 1 over 1 plus the open loop transfer function, all that times the input. Now let me copy this because I'll use it a lot during the video. Now let's suppose that L of S has no integrators. That is, neither the plant nor the controller have any poles in the origin. So L of S is equal to some k times the terms with all the zeros, S over Z2 plus 1 times all the rest of zeros, and here all the poles. I'm writing it in the standard form. Okay, what poles and zeros are these? The poles and zeros of both the plant and the controller. And K here is just the gain of the controller times the gain of the plant. Now, according to what we saw in the last video, we're interested in the steady state errors and their standard inputs. So let's begin with the step function. What is the steady state error like when the input is a unit step? That's pretty easy to calculate, since, as we know, having a step input means that R of S is equal to 1 over S. So we can apply the theorem straight away. ESS for a step is our formula when I have here 1 over s. Now this cancels out with this, and this is equal to 1 over 1 plus the limit when s tends to 0 of all of s. But notice that according to this, that limit is just the gain, 1 plus the gain, the open loop gain. So the error is the inverse of 1 plus the open loop gain. As you see, raising the open loop gain, raising k, will reduce the steady state error under a step input. Well, according to this result, if we have this step, I don't know how the what the transient response will be like, but eventually the system will stabilize in some value, which is this ESS. No, the value would be this, and this distance would be the steady state error. Now, let me give you a warning. The system must be closed loop stable in order to apply the final value theorem. So all the roots of 1 plus P of S, C of S, all the roots of 1 plus all of S must be in the left half plane. Otherwise, the limit will be deceptive. So check always that your system is closed loop stable. Okay, let's do now the error under ramp input. So ESS under ramp means that R of S is equal now to 1 over S squared. So this cancels out with this 2 here, and now this S, let me put it here and here, which means that when we apply the limit, this goes to 0, and we have 1 over the limit when s tends to 0 of s all of s. But since all of s when s tends to 0 is k, we have here 1 over s times k, and that's 1 over 0 times k, so 1 over 0, which is infinity. So the error is infinity, and that means that our system is not capable of tracking a ramp. So this is the input, and the output may have some transient, but then typically it won't be able to follow it. It may do something like this. So this distance here keeps growing and growing. Now, if this is true for the ramp input, even more so for the parabola, since now there are three integrators in the reference, and then the limit becomes 1 over the limit when s tends to 0 of s squared all of s, and this is also infinity. This is the steady state error for the parabola. Okay, so much for systems with no integrators. Let's see what happens when C of S, when either C of S or P of S have an integrator. So let's assume that now we have here one S. Well, in that case, the error for a ramp function, no, for a step function is well, again, here we have 1 over s, so this cancels out with this, and now this is 1 over 1 plus the limit when s tends to 0 of all of s, but this all now has a 0 here, so all of 0 is now 1 over k over 0, which is infinity. So this is 1 over 1 plus infinity, and this is 0. So there's no steady state error, and the system perfectly tracks the step. After the transient response, the system tracks perfectly the input. Regarding the ramp function, now the calculations tell us that this is the ramp, this is 1 over s squared, as we did, this is 1 over 0 plus the limit when s tends to 0 of s times all of s. Now this s here cancels out with this s in all of s, and what we get here is just 1 over the isolated gain that, of all of s. Well, k is not the gain, but if we write it in the standard form, well, the k that is isolated, we can call it gain or isolated gain. Okay, so what does this mean? That we can track the ramp function with limited accuracy. So after the transient, we will track, or the system will track the ramp, and there will be some error, this error here, ESS, which in this case is 1 over k. So again, raising k means that this error becomes smaller. Finally, the error under parabola, you may already have guessed that parabola, it has to be infinity, because here we have s cubed, so this cancels with the 3, we have s squared, and this is 1 over the limit when s tends to 0 of s squared times all of s. Now these two cancels out with the integrator of the plant, but we still have some s here, so we have 1 over 0, which is infinity. So again, this system is not capable of tracking a parabola. Okay, I don't want this video to be very long, so I won't repeat the calculations for systems with 2 integrators, but please do them, and you'll find out that for such systems, both the step error ESS for step is 0, and the ramp error are 0. Both of them are 0, and that with 2 integrators, this is the case of 2 integrators, the steady state under a parabola is just 1 over k. Please check this. So now the parabolic error is finite, and it shrinks as the gain of the system rises. So as you see, what makes a difference is the number of integrators in the open loop transfer function. We call that number the type of the system. So the type is the number of integrators, or in other words, the exponent of s here. We usually denote it with capital N. This exponent is the type of the system, but of the open loop transfer function. Remember that. Actually, I prefer to talk about the type of feedback loop. Why? Well, because the whole system may have other elements or even other loops, each one of different type. When we say that a loop is type 1, for example, we mean that in the steady state the output of the compare is 0 when the input to the system is constant, and that it is a constant when the input is constantly changing, or the input is a ramp. But we're referring to the loop, just the loop, not to the whole system, if it is more complex than this one. And in fact, these results we just got are true in general for systems with non-unity feedback. For example, with this H of S, this sensor dynamics. But they are true as long as we consider that these errors here are referring to the acting error. So the acting error, for example, under a step input of a system type 1 will be 0. By the way, when we include this, then the open loop transfer function is P times C times H. This is the definition of the open loop transfer function. Okay, so in these more complex cases with non-unity feedback, having a small acting error is a prerequisite to achieve a small actual error. And one thing we can do is to multiply the feedback system by an element that we'll call the prefilter, so that some element which fulfills f of 0 equal to h of 0. As long as we do this, having a small ea of s will imply having a small e of s. Okay, all this will make sense through exercises. So in conclusion, more integrators mean greater accuracy. They also bring other nice properties that we'll see in future videos. So according to this, it may seem a reasonable idea to introduce a lot of integrators in the loop. However, we can't do that. As usual in control, there's a price to be paid, and that comes in the form of stability. One of the effects of rising the loop type, that is of adding integrators to the system, is to drag it closer to the instability, or even to make it unstable. So we are limited in the use of integrators. In fact, hardly ever do we find feedback loops with types greater than 2.